So why do we even need a database? Why can't we just write our data straight into a file? Let's actually try that. We'll keep a shops ledger in one file, and every sale goes in as one more line. Now, two cashiers are both serving customers, and they both go to write at the same moment. So the two lines land on top of each other, and we end up with half of one sale mixed into half of the other. Okay, so we fix that with a lock, and only one person can write at a time. That works, except now our second cashier is just standing there waiting. Then the power cuts out, right in the middle of somebody writing. And that's worse than losing a sale, because now there's a sale sitting in the file that's wrong, and nothing in there tells us which one it is. Now somebody asks us something simple, like which customer spent the most last March, and to answer it, we have to open the file and read every single line, every single time. So we've hit three problems there, and they're basically what a database has to do. It has to survive a crash, it has to let people work at the same time, and it has to answer a question without reading everything. Two of those three already have a name. We call them ACID. The third one isn't part of ACID at all. That one's an indexing problem. So where does Postgres actually put a row on the disk? We think about Postgres in rows, but Postgres actually thinks in pages, and every page is 8 kilobytes. The whole database is just an array of them. So let's picture one page as a box, and the box never changes size. Now Postgres needs to find any row in there without reading the whole box. So it keeps a little directory at the front, and each entry just points at one row. The rows themselves go in from the back, and they fill towards the middle. That's why a page fills from both ends at once. The directory grows down, the rows grow up, and when they meet, the box is full, and Postgres starts a new one. Now let's open one row. Before any of our data, there's a small header. One field in there says which transaction created this row, and another says which transaction deleted it. And what if something's too big to fit? A whole paragraph of text isn't going into an 8 kilobyte box. So Postgres parks it somewhere else and drops a little ticket in the row instead. That's why we can put a megabyte of text in a column and the row stays tiny. So Postgres doesn't really move rows around, it moves pages. A read pulls a page, the cache holds pages, and crash protection works on pages. And we've got thousands of these boxes now. So how does a query find the right one? So we've got thousands of these boxes, and we want one row out of them. There's really only two ways to do that. We can walk the shelves and open every box, or we can look it up in a catalog. The catalog is an index, and in Postgres, it's almost always a B tree. Each level narrows things down, so a few hops and we're at the entry we wanted. But the entry isn't the row. It's just a pointer to the box the row sits in, so we've still got to go and fetch that box, and that's a second read. So why doesn't the index keep the data too? Because the index has no idea whether that row is even visible to us. That lives in the box, never in the catalog. If we only want 3 rows, the catalog wins easily. But if we want half the table, then reading the shelves in order beats a million jumps. Something inside Postgres has to make that call, and that part is called the planner. It puts a price on both options. A page it reads in order costs 1. A page it has to jump to costs 4. And 4 is generous because a real jump is much slower than that. But Postgres assumes most of those jumps will find the page in memory anyway, so it charges them less. So the planner's most important number isn't really about our disk at all. It's making up for memory it can't measure. And when the planner skips our index, it usually isn't broken. It just guessed wrong about how many rows we'd get back. And we can ask it to show it's working. The command for that is explain analyze, and it prints the guess and the real number side by side. If those two are far apart, that's what we go and fix. But all of this assumes our data is still sitting there on the disk. It might not be. A disk doesn't write our whole page in one go. It works in much smaller chunks of its own, and one page of ours takes 16 of them. So if the power dies halfway through, some of those chunks are new, and some are still old. We haven't lost the row, but the row we've got is now wrong. So we do what the shop ledger needed. Before we touch anything, we write down what we're about to do in a separate log that only ever gets added to. Then we go and change the page. If we crash, we just replay the log. That's the write-ahead log, and atomicity comes free with it, because a transaction that never made it into the log simply never happened. But the log doesn't fix that torn page. Replaying a change onto a page that's already garbage just gives us more garbage. Every so often, Postgres writes everything out and marks a safe point in the log. and that's called a checkpoint. The first time it touches a page after one of those, it copies the whole page into the log. It copies not just the change, but the whole 8 kilobytes, so there's always a clean copy to replay onto. So yes, Postgres writes a lot of our data twice, on purpose, and it does that by default. And there's two settings here that look like the same dial and really aren't. fsync is what forces our writes all the way down onto the disk. Synchronous commit is what makes us wait for the log before Postgres says yes. So if we turn off fsync, a crash can corrupt the database beyond repair. But if we turn off synchronous commit, it can't. We might lose the last few seconds of transactions, but what's already on disk stays fine. Losing a few transactions and corrupting the whole database are completely different problems, even though the two settings look almost the same. So now our database can survive a crash, but it still can't handle two people at once. So how do we let two people work at the same time without them getting in each other's way? The obvious answer is a lock. While we're reading a row, nobody else gets to change it. That does keep everything correct, but it's slow because one long report can hold up every writer behind it. So Postgres doesn't do that. Instead, it never erases anything. When we update a row, the old version stays exactly where it was. Postgres writes a new version, and it marks the old one as dead. And those are the two fields we saw earlier. One of them says which transaction made this row, and the other says which transaction killed it. So every transaction gets its own view of the data, frozen at the moment it started. Postgres calls that a snapshot. A transaction only sees the versions that were current at that moment, and it ignores anything newer. That's how readers never have to wait for writers, and writers never have to wait for readers. Which also means our update wasn't really an update. Postgres inserted a new row, and it marked the old one as dead. Now, we've still got to decide how much of other people's work a transaction is allowed to notice. Those settings are called isolation levels, and they show up in almost every database, not just this one. The easiest way in is to look at what can actually go wrong. The first problem is reading a change that gets thrown away. Somebody updates a row, we read it, and then they roll back. We've just read a value that never really existed. Postgres never allows that one, at any setting. The second problem is asking the same question twice and getting two different answers, because somebody committed a change in between. And the third is running the same search twice and finding extra rows the second time, because somebody inserted them while we were working. So an isolation level is really just how many of those we're willing to live with. Read committed is the default, and it allows the second and the third. Every statement gets a fresh look at the data, so the answer can change underneath us between one statement and the next. Let's see what that costs us. Two people are buying the last seat. They both check and the seat is free. They both book it. So we've sold one seat twice, and nothing reported an error, because neither transaction did anything it wasn't allowed to do. Repeatable read gives us one fixed view for the whole transaction instead, so both of those problems go away. And there's a Postgres detail here worth knowing for an interview. The SQL standard says repeatable read is still allowed to show us those extra rows appearing. Postgres doesn't allow it. Its version is stronger than the standard actually asks for. Serializable goes further again, and makes everything behave as if the transactions had run one after another. But the stronger levels come with a cost that catches people out. Postgres can decide our transaction isn't safe to commit, and it cancels it. So our application has to notice that and run the transaction again. Which brings us back to those two people and one seat. There's a few ways to stop it, and they all come down to making one of them lose. We can lock the row while we read it. We can write the booking so it only succeeds if the seat is still free. Or we can move up to serializable and let Postgres spot the clash for us. So atomicity and durability came from the log, and isolation is what we just built. Together, that's ACID. The C is the odd one out. In ACID, consistency just means the database keeps the rules we gave it, like not null or a foreign key. The rule that our balances add up to 0 is still ours to keep, not the database's, which makes asking whether Postgres is ACID compliant a strange question. The honest answer is that it depends on the isolation level we picked, and the default one allows the exact problem we just watched. So we can handle 2 people now, but every one of those updates left a dead version behind. And so far, nobody has cleaned any of them up. So let's delete 1,000,000 rows, and then look at the size of the table. It hasn't gone down at all. That's because Postgres didn't really remove anything. Deleting a row just marks that version as dead, and a dead version has to stay on disk while any transaction might still be allowed to see it. So they pile up. Our table fills with rows nobody can see, and the indexes pointing at those rows fill up too. Vacuum is the job that clears them out. It goes through the table, finds the versions nobody can reach anymore, and marks that space as free for new rows. But the file on disk doesn't shrink. That space goes back to Postgres, not to the operating system, so the table stays exactly as big as it ever got. There's a stronger version called vacuum full that does shrink the file, because it rewrites the whole table from scratch. But it locks the table for as long as it runs, so on a large table in production, that's a planned outage. Vacuum also has to decide what nobody can see anymore, and it does that by looking at the oldest transactions still open anywhere in the database. Postgres calls that the X-min horizon. So one connection that opened a transaction an hour ago and then went idle will hold that horizon in place. Every version created since then has to be kept, just in case that connection looks at it. Our writes carry on, the dead versions build up, and vacuum runs on schedule and frees almost nothing. There's a harder limit as well. Every transaction gets an ID, and those IDs are only 32 bits wide, so eventually the counter runs out and starts again from the beginning. Postgres handles that by marking old rows as permanently visible, which it calls freezing. But if freezing falls too far behind, Postgres stops handing out new transaction IDs altogether. It would rather go read-only than let our old data disappear. And that's still how Postgres works today, in version 18. There's a proposal to make those IDs 64 bits wide, but it hasn't shipped. Postgres was designed at Berkeley back in 1987, and one of the decisions they made was that it would never overwrite data. Bloat, vacuum, and wraparound all come out of that one choice. But we've only got one machine so far, and if its disk fails, we'll lose all our data. We've already got everything we need for replication. We just haven't used it that way yet. The log is an ordered list of every change we made. So we send that log to a second machine, and that machine replays it, and now we've got 2 copies of our data. The machine taking our writes is called the primary, and the copy is called a replica. By default, the primary doesn't wait for the replica. It commits, it tells us the write succeeded, and it sends the log across afterwards. So the replica is usually less than a second behind. Usually, though, if the primary's disk fails, some transactions we already committed might never have reached the replica, and however far behind it was is how much data we lose. So replication lag is really a measure of how much we would lose if the primary failed right now. And there's a quieter version of this that shows up long before anything fails. Someone posts a comment, the write goes to the primary, the page reloads, the read goes to a replica, and that replica hasn't got the comment yet. So it looks like their comment vanished. Nothing has actually broken, no alert goes off, and the bug report just says, the site ate my post. So choosing which reads can go to a replica is a correctness decision, and we have to make it deliberately. Postgres also does something here that a lot of other databases don't. Every connection we open gets its own operating system process, with its own memory, rather than a lightweight thread inside a shared one. So the default connection limit is 100. It's tempting to push that to 5,000 when we need more, but 5,000 processes all competing for the same shared memory won't do 5,000 times the work. Most of the machine's time ends up going into managing the processes themselves. So we put something in front that keeps a small set of connections open and shares them around, and that's called a pooler. Almost every Postgres setup of any size ends up running one, and that's more or less the whole system now. Storage, crash recovery, working in parallel, cleaning up afterwards, and a second copy of everything. So what is Postgres actually bad at? There's 3 things, and each one comes from a decision we already watched it make. Write-heavy tables keep growing because Postgres never overwrites anything. That's the cost of letting readers work without ever blocking a writer. Connections are expensive because each one is a whole operating system process. That's the cost of the process model we just looked at. And writes only ever go to one machine. That's the cost of keeping a single copy that everything agrees on, and past that point, we're building the scaling ourselves. Now let's work backwards from any one of those. Why do we need a pooler? Because there's a process for every connection. Why has the table grown so much bigger than the data inside it? Because nothing gets overwritten, so an old version has to stay while anyone might still see it. And why might anyone still see it? Because a reader takes a snapshot instead of a lock. And why not a lock? Because a lock makes readers and writers wait on each other, and that's the thing we were trying to avoid in the first place. So the whole chain runs from the page, to the log, to the snapshot, to the dead version, to vacuum, to the replica, to the connection. So when something in Postgres surprises us later, we can usually trace it back to one of these.